All right, so the next thing that I want to talk about is what's called the Monotone Convergence theorem. And this is a result about real valued sequences. So in other words, sequences whose outputs are always real numbers. So in order to do this, we just need a few definitions. They're not hard definitions. There's just a few of them. It should be a pretty clear thing. So I think it's clearest if I just give all the definitions and then we'll talk about it. So there's the monotone convergence sequence. So first I want to tell you what monotone means. So there's all sorts of, I'm gonna do this slightly differently than the book does. I'm gonna define a sequence to be strictly increasing if each of the terms, and again, these are real valued. Okay, so in other words, the sequence is a real number. You cannot talk about inequalities with complex numbers. But a real valued sequence A sub n is strictly increasing if a sub n plus 1 is greater than or equal to a sub n for all n. Okay, so in other words, if each of the terms is getting larger and larger and larger, that's a strictly increasing sequence. And excuse me, when I say strictly, what I mean is the inequality is strict. It's strictly greater than a sub n. So for example, you could have something like n minus 1 over n, something like that. And I'm not going to give too many examples here, but if you were to have something like n minus 1 over n, this is a value that's getting bigger and bigger and bigger. So when n is 1, you get 0. When n is 2, you get 1/2. When n is 3, you get 2/3, and so on. Each value is just a little bigger than the rest. Strictly increasing does not force the sequence to go to infinity, right? So anyways, so that's strictly increasing. And then from here, you can see that there's going to be 4 definitions. There's just increasing. So a sequence is going to be called increasing if a sub n plus 1 is greater than or equal to a sub n. It's going to be decreasing if a sub n plus 1 is less than or equal to a sub n, and then strictly decreasing. So this is strictly decreasing if a sub n plus 1 is less than a sub n. So hopefully, I mean, I haven't written out all the details, but hopefully you understand precisely what I mean. These are all statements that are true for all n, and for all n. Okay, so that's what strictly increasing, strictly decreasing, increasing, and decreasing all mean. Now, if a sequence A sub n is either increasing or decreasing, it's called monotone. Okay, so A sub n is called a monotone sequence. Okay, and so if the terms always get larger or if they always get smaller, the term is monotone. Monotone meaning that the sequence only moves in one direction. Either they all get larger or they all get smaller. If A sub n is either strictly increasing or strictly decreasing, so strictly increasing or strictly decreasing, then A sub n is strictly monotone. Okay, so when we say strict, all we mean is that when we're talking about an inequality, we don't allow equals. So it's just a strict greater than or strict less than, not a greater than or equal to or less than or equal to. Okay, so we're not allowing the equality part. That's what strict means. Okay, and so that's monotone. Okay, so that's monotonicity and strict monotonicity, which the book talks about just a little bit. Now, it turns out that, and I'll call this a theorem. In fact, this has a name, so let's just call it by its name. This is called the Monotone Convergence theorem. I forgot the word monotone. So the Monotone Convergence theorem. And what this says is that every monotone and bounded, so every monotone and bounded sequence converges. Okay, bounded means that, so bounded means that And actually bounded makes sense. Monotone only makes sense for real valued sequences. Bounded is a idea that makes sense for all sequences. Bounded just means that these values a sub n are less than or equal to some finite number m for all n. Okay, so if there exists a value m so that the sequence satisfies this, then this is true. And here m is of course a real number. Okay, so anyways, every monotone and bounded sequence converges. That's the monotone convergence theorem. And that's not too surprising if we think about this, right? If you have a sequence like n minus 1 over n, just to give an example here. So this is n minus 1 over n. What's going to happen here is that when n is 1, we get 0. Okay, so when n is 1, we get 0. That's actually, I want to take that back. So let's say this is our n, and this is our a sub n. So when n is 1, we get 0. When n is 2, we get 1/2. When n is 3, we get 2/3. When n is 4, we get 3/4, and so on. And it turns out that each of these values here is always going to be less than or equal to 1. Okay, so note that here a sub n is greater than or equal to 0. We don't need any modulus signs. It's a real valued, positive real valued sequence. So a sub n is always less than or equal to 1. I mean, let's just put the modulus signs there just to be thorough. But each of the values in the sequence is going to be less than or equal to 1, and it's strictly increasing. And you can check that it's strictly increasing. I'm not going to worry too much about that. And therefore, it's going to converge. And in this case, it's going to converge to 1. Okay, and in fact, the limit of n minus 1 over n as n goes to infinity is 1. Okay, or if you like to do it using the other notation that I showed you, n minus 1 over n goes to 1. Okay, and so this is an example of a monotone bounded sequence. It happens to converge to 1. The fact that this was bounded by 1 and that it converges to 1 is, I don't want to say it's a coincidence, but it doesn't always have to be that case. For example, all of the values here are also less than or equal to 2, but that doesn't mean that the sequence converges to 2. Okay, so the upper bound that you're going to have, if you have an increasing sequence anyways, the upper bound can be at the limit or larger than the limit. In this case, our upper bound could have been 1 or any real number larger than 1. Okay, so it could have been 5. All the values in the sequence are less than or equal to 5. That's still true. The sequence still converges to 1. Okay. So let's think about what this means. I'm not going to actually walk through and prove this theorem in general. Yeah, I don't really want to do that right now. And so the proof is not hard, but yeah, but just since this is kind of old news or something that in principle you've seen before, you can kind of look up the proof on your own if you'd like to. Yeah, so let's do a few examples here. What I was going to say before is I don't want to prove it, but let's just think about what this means. When you have sequences which diverge, in other words, the ones that don't converge, we had the sequence where the values of the sequence were, so these are complex numbers, so that's not a great example, but if you were to have a sequence that's, say, 1, -1, so here, if you were to have a sequence that's sine of pi n over 2, as say n goes from starting at 0, then a sub 0 is going to be 1. I'm sorry, a sub 0 is 0, a sub 1 is 1, a sub 2 is sine of pi, which is 0, and then -1 and 0 and 1. And so even though here the terms are bounded, even though the sequence is bounded, I mean, this is not going to diverge. It's not monotone. Okay, so it doesn't have to converge. So that's one example. The other example that we saw was something like if we had, say, 2 to the n. Okay, here this is monotone because 2 to the n is an increasing function. So the larger value of n we plug in, the larger value we get out. The problem is that it's not bounded. Okay, so both of these diverge. Okay, so this also diverges. Anyways, one example that I think is going to be particularly helpful here is to think about a sub n as the sum of 1 over k factorial. This is an example that the book does as well, but I'm going to do it slightly differently. A sub n is the sum 1 over k factorial as k goes from 0 to n. So in other words, this is the value 1 plus, well, 0 factorial is 1. So that's 1 over 1. So this is 1 over 1 plus 1 over 1 factorial, which is also 1 over 1, plus 1/2, plus 1 over 3 factorial, which is 6, all the way up to 1 over n factorial. So here a0 is 1, a1 is 2, a2 is 5 halves, right? Because that's 1 plus 1 plus 1/2. a3 is going to be, let's see, 1 plus 1 plus 1/2 plus 1/6. I don't know why I do this to myself. Plus 1/6. So what is that? Normally I have your help for all this algebra here. This is 5 halves is 15/6. So this is 16 over 6. So that's 8/3. Okay, and I'll stop there. Okay, so that's a3. So this is how the sequence is defined. Now, of course, a sub n is increasing. It's actually strictly increasing. And of course, that's going to happen. And this is going to be one thing that we'll talk about constantly when we have series. If the thing that we're adding each time is greater than or equal to 0, then the overall sequence is going to be increasing, right? Because here you have kind of a recurrence. You have all the previous values plus this new positive term, so that's going to be slightly bigger, right? So a sub n is increasing. A little bit more surprising is that a sub n, I shouldn't say surprising, but a sub n is bounded. So for example, you can prove using induction that a sub n is less than 3 minus 1 over n for all n greater than or equal to 1. Okay, so a sub n is less than 3 minus 1 over n. In particular, the values of the sequence are always less than or equal to 3. Okay, so it is bounded above by 3. And this means by the monotone convergence theorem, the sequence a sub n has a limit. It turns out that this limit happens to be e, which is 2.7 whatever, 2.71828. Yeah, so that's what that monotone convergence theorem says. Okay, so here we have an increasing bounded sequence. That's really all that I wanted to say there. Okay, so this sequence happens to converge to E. Okay, all the monotone convergence theorem says, I just wrote this poorly and I just want to clarify. All that the monotone convergence theorem says is that this sequence converges. And then we have to do a lot more work to figure out that it actually converges to E. Okay, so that's not an obvious statement. We need to do a lot more work to figure that out. Or if you know power series, you know that this is e to the 1. And so this is really just the power series there. There's other ways that you could actually define this, but other ways that you could actually verify this depending on how you define the number e, but this is fine. Okay, so this sequence happens to converge to E. All right, so just a little bit of a intuition check, just so that we can all be on the same page here. If we were to have the limit of a polynomial over an exponential over some, say, c to the n, where c is greater than 1, this is going to be 0. No matter how big the polynomial is, exponentials win every time. If you were to have a polynomial over a factorial, that's going to be 0. Again, factorials grow faster than any exponential function. I think I said polynomial before, but polynomials grow slower than exponentials. Exponentials grow slower than factorials. The factorial grows slower than n to the n. Okay, so that's also going to be 0. So it makes sense, right? If you think about n factorial as n times n minus 1 times n minus 2 all the way down to 1, but n to the n is n times n times n times n every time. So each of these is going to get smaller and smaller. So this is going to tend to 0. And in fact, I just want to say a little bit more about this. The fact that polynomials grow slower than exponentials also tells you that logs grow slower than polynomials, right? So if you take a log of both of those, then the log of a polynomial is basically log n. So you would have natural log of n, and then any quantity of the form n to the epsilon, if epsilon is positive, this is going to also be 0. Okay, so here epsilon has to be positive. Okay, so logs grow slower than any power of n, any constant fixed power of n. Okay, so they grow excruciatingly slowly. So the natural log grows slower than n to the 1 over a trillion. Okay, but I do just want to talk a little bit about this last term, the n factorial over n to the n goes to 0. And so I want to show you, I'm not going to go through, there's quite a bit of detail that goes into what's called Stirling approximation. So I'm not going to actually do that, but what I'm going to do is I'm going to verify that n factorial does grow faster than any polynomial, but slower than n to the n. Okay, and so the way that I want to think about this, and this is going to just lead us into some ideas that we're going to have to consider in a second anyways, but let's take the log of n factorial. N factorial is a product. When we take logs of products is the sum of the logs. So this is going to be the sum of the natural log of k as k goes from 1 to n. And this sum can be approximated by an integral. So this is going to be approximated by the natural log of x dx. And here, this approximation, what I mean is that they're approximately equal to, and I'm not being precise here. But if you were to have the natural log of k, this is going to look like something like this. It's going to be a really slowly increasing but unbounded sequence. Okay, so this is going to be unbounded, even if it looks like it's bounded. So it's eventually going to get as large as you want. And the integral, you can think of as kind of connecting all of these with a continuous curve. Okay, so let's say we go up to n. On the other hand, the sum is going to be approximated by the sum of the rectangles. Okay. And I didn't draw this very well, but you can always approximate an integral with a sum and vice versa. Okay, so here they're approximately equal to, and to figure out exactly how they differ, you can kind of play around with the extra bits here. Okay, and so this sum is going to be, I need to be a little bit careful here. The sum is going to be, they're approximately equal. I think I would want the sum, I would just have to go and think about this very carefully, but the sum from 1 to n is going to be, I think, up to here. Okay, something like that. And so this integral might be a little bit more, and then you can bound it, but it doesn't matter. So I mean, we can make this as rigorous as we need to, but we don't need to right here. Now the integral of the natural log of x, if you apply integration by parts, you get x natural log of x minus x evaluated from 1 to n. And so that's going to be, since I don't care about constants, this is going to be n times the natural log of n minus n minus, plus 1. But who cares? We're already estimating, so we don't need the plus 1. Okay, so when n is large, that plus 1 is negligible. And so this tells you that log of n factorial grows approximately like n log n minus n. And so if we exponentiate both sides, again, I'm being super careless with how precise this is, but I just want to give you this idea of how it works. N factorial is going to be approximately equal to e to the n natural log of n minus n. So that's e to the n natural log of n over e to the n. And e to the n natural log of n is just n to the n. So this is n to the n over e to the n. In other words, n factorial is going to be approximately equal to n over e to the n. So in other words, faster than any fixed exponential, because n gets arbitrarily large, right? So if n gets arbitrarily large, so does n over e, and then this is bigger than any fixed exponential, but slower than n to the n, because if you were to have n to the n, and if you were to divide this by n to the n, you get 1 over e to the n, and that's going to go very quickly to 0. Okay, so this is much smaller than n to the n, much faster than a fixed exponential. And in fact, there's what's called a Stirling approximation, and that tells you precisely how this is, precisely how the factorial grows. So it turns out if you take the limit as n goes to infinity of n factorial, all divided by, I need to just be very careful about this with constants here, all divided by some constant over square root of n times n over e to the n. This is going to be 1. And I think I may have the constant wrong, but just look it up. The point here is that our terrible estimate, where I wasn't very careful with our bounds, was not too far off from the truth. We're just missing a dividing by square root of n. Okay, which basically means that before we exponentiated, we were off by very little, right? If after we exponentiate, we're off by a square root. Okay, so you can look up precisely what that is. I have a feeling that this might not be correct. So let me actually, before I regret that, let me just erase it. Okay, but that's basically all I wanted to say so far about limits.